Hello and welcome back. This might be one of the more complicated questions in electrochemistry. We've got this abbreviated cell notation. We have some half reaction voltages. We have a temperature, and we're asked to calculate the cell potential for this chemical reaction. Now, I normally ask this kind of question to my class at standard temperature because there's enough going on here. Now, if it's not at the standard temperature, you've got to plug everything in. So, we have the RT over NF, okay, times the natural log of Q. So in case you're watching and you have this really complicated problem, that's where you would have to plug in the temperature if it was some weird temperature. Now, it turns out this all simplifies to the Nernst equation. I'll write this here in case you want to look more about it. Nernst equation. So E is equal to E naught minus voltage divided by N times the natural log of Q. Now, I like to use the natural log because Ln is used in thermochemistry, which is the chapter prior, and it's used in a lot of different places. Now, this traditionally was used for pH meters, and since pH is a log scale, you might see this in a textbook, and that's fine, whichever method you use, but the constant's going to be slightly different, okay? And again, I'm telling you all of these varieties because we have many different people that watch my YouTube videos and might like to know, well, which equation do I use, okay? So this might be in your book, okay? And this is the one that's in my class and in my text, the OpenStax chemistry textbook, and what I use, okay? So we're going to use this one. Now, when we look at this, we need to know the standard cell potential, so we'll calculate it from this table over here. We need to know what N is, and remember that's the, from the electrochemical equation as well. So let's write the electrochemical equation. Again, what we need to do is read this from left to right. So if we've got chromium, which is a metal, going to form chromium, which is positive 3, okay? We place electrons on the more positive side, okay? Because a charge of 0 is going to be equal to a charge of plus 3 plus a charge of minus 3, okay? So the charge is balanced on both sides of this equation. Nickel plus 2 is going to nickel metal. And again, we put electrons on the more positive side. We're going to put 2 electrons over here. Okay, 2 electrons over there. Now, remember what we need to do in order to get these equations to correctly come together. We need to make sure that we find the common multiple of the number of electrons. So 2 times 3 is going to be equal to 3 times 2, or 6, okay? So we're going to have 2 chromium going to form 2 chromium, and we have our 6 electrons there. I'll switch pen colors here. Now for the nickel guy, 3 times 2 is 6 electrons. 3 times the nickel. Move this up a little bit. And that reacts to form 3 nickel. Okay. So remember, when we add these two equations together, the electrons cancel out, and that's the purpose for doing that. And now we have our balanced redox reaction. So we take all the left-hand side stuff, and that's going to form all the right-hand side stuff. Now there's a bunch of 2's and 3's in this problem. Be careful about the charges and the coefficients and all of that. Now if we look carefully at the situation going on here, we know from the formula that N is now equal to 6, because that is equal to the number of electrons that cancels out in this balancing method for getting your balanced redox method. Okay, so now we need to find out what the E cell is. All right, E cell, and that comes from the half reaction voltages given to us in the table on the right. So we've got chromium going to chromium 3 plus. That's this reaction reversed. So we want to reverse the sign of this half reaction. So the E cell for the E for that reaction is going to be positive 2.357. Okay, and that's because we have chromium solid on the left here, but it's on the right here. We have chromium 3 plus on the right, but here we have chromium 3 plus on the left. If you need to flip a reaction to match your reality, you need to reverse the sign. Now for the nickel reaction, I'm going to switch to maybe a dark green here. We have nickel 2 plus on the left, and we have nickel on the right, so we don't need to reverse the sign of the voltage for this half reaction. It's 0.518. Okay. Now to figure out the cell potential voltage, we just add those two up, right? So the E cell is going to be equal to 2.357 plus 0.518, and the units there are voltages. Okay, 2.357, add 0.518, and I get 2.875. Okay, so I know both of those quantities. Now how do I find Q? A Q, remember, is products over reactants, concentrations. Okay, so I made a mistake in my half reaction here. So I had 3 nickels. That should have been a solid here. All right. Now, when we're figuring out what Q is, remember that solids don't enter into the equilibrium expression. It's only aqueous things. So on the product side, we have chromium 3 plus. We have 2 of those, so it's squared. On the reactant side, we have nickel 2 plus, and we have 3 of those. That's cubed. Okay? So that's how I'm going to figure out Q to plug into the Nernst equation. Now, I need to scroll all the way up to the top to figure out what those concentrations are. Okay, I'll highlight this in, I don't know, yellow here. Okay? So the chromium is 3 plus is going to have a concentration of 0.615, okay? And the nickel 2 plus is going to be 0.288, all right? You got that? So let's scroll back down. Let me verify that that's correct. So we said it was 0.615 for the chromium, 0.288 for the nickel. All right. So now we're going to evaluate this, and this is how I get my Q. All right. 0.615 squared divided by 0.288 squared, and that's equal to 4.56. It's showing up on my calculator. Okay. We come back again to the Nernst equation. E is equal to the E cell times the natural log of Q. All right, so the E cell, we said, let's go find out what that number is, was 2.857 in dark green up there. Okay. 875, I meant to say. Okay. And then the rest is a little bit of constants here, so 0.0257 volts. And then in purple here, we said that N was 6 when we balanced the half reaction, right? And then in orange, we have the natural log of Q, which is, 4.56. So it's kind of like 3 different problems all in one. And I'll do this right-hand portion first. So 4.56, hit the ln button on your calculator, times 0.0257 divided by 6, okay. And that's 2.875 volts, okay, minus 6.499 times 10 to the minus 3. Let me double check that here. Yes, okay, so that whole portion right here is 6.499. All right, so we're going to subtract that from 2.875 volts. And I get 2.869 when I round that 8 up. All right. So because of the non-standard concentrations of the chromium and nickel ions, the voltage is not 2.875, it's a little bit lower, 2.869 volts. So that's how you do this problem. Let's review what we had to do. First, we had to use the abbreviated notation to figure out what the redox equation was, and we figured out N was 6. From the balanced redox equation and the half reactions, we could figure out the E cell. And then from the balanced redox equation, which we had to get in this problem, then we could write an expression for Q in terms of the concentrations, and then finally we plugged it into the Nernst equation to find the final answer. Please give a thumbs up, like the video if you thought it was helpful, and please consider subscribing. Have a great day.